Welcome to this presentation, Utility Functions Part 1. This is a continuation from the introduction to utility functions that was covered in the last module. In this presentation, we're going to continue our discussion on utility functions. Why do we use utility functions? What's their purpose? Up to this point, when we dealt with, when we were creating a decision tree, we had to solve for the expected value at each node. Typically, these are monitoring values. So we're really calculating the expected monitoring value. On a typical outcome, the outcome is, for example, the net payoff is $10,000. If you go to a different route, it's $20,000. Based on some probabilities, you take the expected value, and that is some kind of monitor value. And that's the way we've been dealing with most of these cases. But what if we're dealing with factors that really it's not really directly related to some monetary value, or it's hard to quantify basically. So how do we deal with these? How do we deal with decisions with non-monetary factors? And also, how do we incorporate a person's attitude towards risk? Basically, a person's preference. How do we account for these factors? So, for example, a person's preference for red over blue, or the person's preference for a cooler weather versus a sunny weather. If you were to account for these kind of factors, how they affect your decision. In a nutshell, you're trying to convert these non-monetary values into some kind of quantitative measure so that you can get an expected value in the end. We're going to now revisit the hosting a party decision that was explored in the last presentation. There was uncertainty on the weather. We didn't know whether the weather was going to be sunshine or rain, and our decision maker Sam had to decide whether to host a party outdoors or at the porch or indoors. And there were 6 different outcomes in this scenario. Let's say Sam has a friend named Chris who faces the same problem. So we already solved this. We analyzed the situation for Sam using the probabilities and using the different preferences for Sam. Now let's look at the problem from Chris's perspective. Chris also has the same probability assessment for the weather. So the decision tree will look very pretty much the same at this time. Everything's the same, but Chris, although very similar to Sam, will have a different set of preferences. So we continue by asking Chris to identify the best prospect and the worst prospect. And again, Chris has very similar preferences to Sam. So Chris will also set the best preference as outdoor sunshine and the worst preference to outdoor rain. And then we ask Chris to rank the other outcomes. And Chris is very similar to Sam. So the ordering of the outcomes are exactly the same. But the difference here is if you look at the preferences, these values here, this column, okay, do differ from this column. We've set the dollar values equivalent, but the preferences themselves are different. Right? For each outcome, Sam's and Chris's preference do vary. So if you look at Chris's preference probability and then Chris's dollar value, so the assumption here is that we've elicited these dollar values in the same way we did for Sam, and you can look at a detailed explanation on the previous presentation and how this process works using a set of lotteries. So we get this result, and we can plot Chris's preferences probably versus the dollar value and fit a curve like we did in the past for Sam. And this is what the curve looks like. So we've left Sam's curve there, and we have Chris's curve as well. And Chris's curve is the flatter diagonal there in orange and the square markers. This is Chris's U curve. Similar with Sam, this is Chris's U curve. Sam's U curve, we remember in the past, is those the blue line above Chris's. The Chris's curve is a diagonal,
where we can describe this curve as u equals to x divided by 100. This curve is very special because this curve is what's called risk neutral. This is a risk neutral curve. Chris is indifferent between a 50-50 chance of winning $100 and getting $50 with a 100% start date. It's a very specific case here. This is a diagonal. And again, it looks very, very different from Sam's curve. So if you were to show this on a lottery situation, so if you had a 50% chance of winning $100 and a 50% chance of winning nothing, Chris's preference is a 1 for $100, and the worst outcome here is a 0. So the preference value is 0. This is equivalent to getting basically $50 with 100% certainty. So this is the equivalence between these two lotteries. Similar to Sam, we're gonna calculate the U value for each prospect for Chris. So we're gonna draw the tree. So we're gonna go through the same process, rain, sunshine for each. Now we've already elicited the U value, and also now we have the curve to use to obtain these U values. Okay, so based on those U values, we can get the equivalent dollar amounts, right, using that Chris's U curve. Okay, so that's where we get these dollar equivalents for each one of those outcomes. And then now we're ready to solve for each one of those nodes. So we'll start with node A. Okay, so we have the probabilities unchanged as before. Okay, we'll start with node A. Okay, node A again is simply we're just getting the expected value. So the U value, it's going to be 1 here, 1 times 0.4 plus 0 times 0.6. So this value will be 0.4. Based on the U value of 0.4, we could now go to the U curve and to figure out the corresponding X value. So this is a very simple U curve where it's simply diagonal. So Ux is simply X over 100. So you can get this directly and find that the X value here is 40. 40 over 100 is 0.4. So therefore, we know the equivalent dollar value for that outdoor option, is $40. We're going to now repeat for the other options here. If you look at node B, we're going to find the expected utility value, which is 0.9 times 0.4 plus 0.2 times 0.6, okay, which is 0.48. So again, we need to find the corresponding value on the x-axis for this U value of 0.48, which is simply going to be 48. Okay, so now we know this is equivalent to $48. Okay, we repeat for node C. It's going to be the expected utility value 0.4 times 0.4 plus 0.5 times 0.6. The equivalent U value here is going to be utility value here is going to be 0.46. We're going to find the equivalent dollar amount, monetary value, using the U curve. So this is just going to be $46. Okay, so this is my result for Chris. So for Chris's case, based on Chris's U curve, the preferred prospect or preferred option is hosting the party at the Porsche. Right, so it yields the highest monetary value. Okay, so this is different from Sam's result, which you probably can recall. I believe it was the indoor option, and again, the probabilities of rain or sunshine hasn't changed, but because of their preferences, the optimal action here is different. Now, taking on the results from both Chris and Sam, we're going to discuss an important topic, which is the attitude to risk using the U curves. So the blue line there represents the U curve for Sam, and the red dotted line there represents the U curve for Chris. And we're going to assume that purple dashed line represents the U curve of somebody else, another third person. The red line there, the red dashed line, is what's called the risk neutral line. This is the diagonal, and Chris captured this diagonal risk U curve. The purple dashed line there is what's called risk seeking, and then the blue line there, the solid blue line, is what's called risk averse. So there's three. We're gonna coin this term: risk neutral, risk averse, and risk seeking. And the U curve, there's basically in a U curve, it reveals a personal attitude or preference to risk. Is somebody risk averse? Is a decision maker risk seeking, or is a decision maker risk neutral? For the risk seeking U curve, okay, which is the purple line down there, the purple dashed line, okay, we can see that the increase in the U value corresponds to a larger increase in dollar value. So if you see let's say a unit increase, let's say a 0.1 increase in the U value on the y-axis, the corresponding increase in the x-axis is much bigger. Right? So, for example, for a difference of this much, okay, this is the dollar amount. Okay, if you were to compare that for a risk-averse person, the difference in the x-axis value, the dollar amount, will be much smaller. Okay, so if you look at just at the purple line, okay, the risk-seeking U curve, we can see that the increase in this U value corresponds to a larger increase in this dollar amount. Okay. For the risk-averse U curve, we can see that the increase in the U value corresponds to a smaller increase in dollar amount. Right? So this right here, this vertical distance corresponds to this region 3, distance 3, results into a smaller increase in the x value. Okay. Some utility functions will have a combination of both a risk-averse and risk-seeking region. So not all U curves are going to have a concave or diagonal, etc. It's not going to have a single profile. It might have a combination, but at different parts of the the U curve, decision maker may exhibit a risk-averse or a risk-neutral or a risk-seeking attitude. So I'm going to give you some examples of risk-averse curves. So in our example, Sam had this risk-averse profile, right? So Sam had a curve that looked like this. Okay. So risk-averse. Some examples of such curves are, for example, the ln curve. So a curve like ln x would have a profile that looks like this: square root of x. Okay. Or x to the power of a, where a is some value from 0 and 1, or negative e to the negative ax, where a is a positive value greater than 0. Okay, these are common examples of risk averse of this type of curve here. Okay, so again, Sam being one of those. Another way for you to check is simply find the second derivative of the U curve. Okay, so if you find the second derivative of the U curve, if it's a negative value, it's going to be a risk-averse profile. If the second derivative is 0, it's a risk-neutral profile. If the second derivative of the U curve is greater than 0, it's a risk-seeking profile. Okay, so that's another way of determining whether the decision maker is risk-averse or risk-seeking in that region of the U curve, or maybe the whole thing, but it could be a combination across the different set of values you're looking at. We can also look at specific parameters to see whether an individual is risk averse or risk seeking. A commonly used risk aversion measure is the Pratt measure, and this is defined by r equals to negative of second derivative of the U curve divided by the first derivative of the U function. Since for risk averse individuals, the second derivative of the U function is negative, so then this parameter will end up being positive. Again, we have this negative symbol here. Since the numerator is negative for a risk averse individual, the entire parameter then becomes positive. So for a risk averse individual, this value will be basically positive. Okay. We'll give you a simple example here. If the U curve is the natural log of x, okay, take the single derivative. So this is the curve of the natural log. If you take the single derivative, it'll simply be 1 over x. If you take the second derivative of it, it's going to be negative 1 over x squared. Okay, so if you find the prep measure here, it's going to be negative. The numerator will be negative 1 over x squared, or the second derivative of the u curve, divided by the first derivative of u curve, 1 over x. So the negatives cancel here, the x's cancel, one of the x's, so the whole expression ends up simplifying to 1 over x. Okay, so therefore, the r value is greater than 0 for all x greater than or equal to 0. So this is again, the natural log of x. If the utility function has a shape, this is a risk-averse individual. Okay. This is the end of the presentation. Thank you for watching.